All right, welcome everyone. Thank you for joining us for our webinar today. I hope you guys are enjoying SmallSat as it looks very different this year for everyone. So we appreciate you guys jumping on. So Sage is gonna have a presentation here for about the first 15-20 minutes, and then we can open it up for a Q&A at the end. So Sage is the COO here at Tether. He's been working here for a few years now, and he has an engineering background. We'll be able to answer any questions at the end here that you guys have about our mesh networking system that we actually have developed already. So Sage, I'll let you take it away.
Okay, thanks for joining us today. So we're here to talk about mesh networking and secure comms for SmallSats. So first, some 101 stuff. What's a mesh network? A mesh network is a bunch of nodes that are actually connected to one another without a hierarchy. So it's not like Wi-Fi where two units actually talk through a base station, or cellular where, again, two cell phones would talk to one another through a cellular base station. But so mesh networking is really one node talking to another and collaborating and working together without the need for an access point or base station. And so why choose a mesh network often comes up. Why don't you pick Wi-Fi or something else? And ultimately, when you're choosing a topology, you have to choose between, there are trade-offs that you have to make between resiliency and performance, speed and cost, and scalability and application. And so, with a mesh network, what it really gives you is the resiliency, the flexibility, scalability, the ability to self-heal and self-form, as well as be able to perform collaborative collaboration between two nodes or do swarm operations, and also there's very minimal infrastructure required, and it's ideal for small sats because of the fairly minimal infrastructure that's required. And so looking back at Earth, you know, when you're looking at mesh networks, you know, one of the main things that makes really working in space very, very difficult is that Wi-Fi, LTE, OneWeb, Iridium, those are all different types of communication systems. But if you look at the distances there, I mean, you're going to really see that ultimately working in space, especially from an RF comms perspective, is a particularly hard thing, because ultimately those distances relate to latency and more power. And those are two things that small sats really don't have much of, right? Power is something that's fairly limited on a small satellite. So, the distances, when you look at terrestrial applications, especially Wi-Fi and LTE, you know, the maximum distances you're talking about are 200 meters or 16 kilometers when it comes to LTE. So, as opposed to space applications where, you know, even OneWeb's mega constellation is about 87 kilometers apart from one another. So there's vast distances to reach there, and that's part of the reason why it takes more power to close the link and have and basically have the same performance, requires a lot more power. And so also, by the way, just as a side note, terrestrial meshes are also, it's going to be on orbit, and you can model that orbit and that behavior, so you'll kind of know where they are. So space-based meshes are actually deterministic, and terrestrial meshes obviously have power resources available. Sure, they're IoT devices, but at the end of the day, you can always plug in another battery to them, which is not something you can do easily to in a space application. And also, obviously, they're relatively close to one another. So a long time ago in a galaxy far, far away, episode 1, the requirements, the Emperor, Customer X came to TUI with a problem to resolve. they had brought every salesperson's worst nightmare requirements document, and that's exactly what happened to us. Our customer came to us and said, "Hey, we know you sell radios, but can you also look at building radios that have mesh networking capability?" And that's where we kind of started this whole process. And so as we started this process, we looked at the market, and really what we found, and just going back to the 1960s and 1970s, is that this is a picture of IBM Irma, and this is the first accounting device that is known to be used with Bank of America. So this device and everything you see in this picture was really what Microsoft Excel does today, fairly simply on your iPhone or computer or your laptop. But IBM, this allowed Bank of America to basically maintain the thousands of transactions they were doing from a day-to-day basis and be able to sum them up and total up all those transactions electronically. But ultimately, the technology of that time was built so that there was only one function. It was very costly. There was special training that was required to operate it. Didn't share any resources well at all. In fact, if you look, there's an actual calculator on the left-hand side of that picture, and they're not interconnected. So this is all this machine could do was basically be Microsoft Excel, and that's all it could do. And in fact, it wasn't until computers were networked where they could actually start sharing resources, and so you didn't need dedicated hardware for dedicated applications. And that really kicked off in the 1970s and 1980s. Looking forward at satellite technology today, satellites today, even in 2020, even the latest and greatest mega constellations are still bent pipe communication satellites and are not interconnected to one another. They still only, if you remember this red box from the 1960s, these satellites still only have one function. They're costly. They still require special training to operate them. They don't share resources, and they're not interconnected. And so, we made a conclusion that, hey, satellites are really analogous to where computers are in the 1960s and 70s, that they don't connect well to one another. They're extremely costly. They're not flexible. Their resources are not shareable. They take up a lot of space. They have only one function or purpose, and that you need special training to operate them. So at least in my mind, I said, oh man, satellites of today really is like mainframes of 1960. So looking at that, we were able to form a plan of how to base our new networking technology. And so our solution was SWIFT-LINQ. It's our mesh network for space applications. And the best part of SWIFT-LINQ is it's available now. It's delivered. It's actually TRL7 software that's riding on TRL9 hardware. It's been integrated with the spacecraft, and it's gone through all the environmental testing. And there's going to be a demo, hopefully soon here, of SWIFT-LINQ by the end of this year. And so SWIFT-LINQ, one of the key advantages of SWIFT-LINQ is it leverages our existing Swift radio platform. It's basically a software application that rides on top of our TRL9 hardware that has been flight tested. We've got over a dozen on orbit now. And so it has flight heritage. And again, the system has been delivered, tested, and integrated into a spacecraft. And so the total solution is TRL7. And again, like I said, it's available today. But what makes SWIFT-LINQ so kind of unique out there is that SWIFT-LINQ isn't just a radio. It also acts as an OSI layer 3 router. So SWIFT-LINQ is based on IP networking technology. So each satellite actually has its own IP address, and our radio with the SWIFT-LINQ application can determine which satellite the data is actually intended for that's being transmitted, and it's capable of performing the hop so that it can get to the end destination of where it's supposed to go. So SWIFT-LINQ really acts is not just a broadcast system, but actually has the ability to route data to its end destination as well. And so SWIFT-LINQ is resilient. It's because it's a distributed system. Data hops from one node to the next with no external management, and that's really helpful because in case of network disruptions, kinetic attacks, network infiltration, or jamming, the network is actually self-healing. Traffic can be rerouted and ensure that data continuity and make sure that the data still gets to the endpoint of where it needs to go. So as part of our roadmap, one of the things that SWIFT-LINQ is going to have is the ability to have software-defined networking functionality. And ultimately here, what we're trying to do is really remove the control plane from the SDN architecture and allow for routing decisions to be made in a centralized location. So the main benefit of SDN for satellite applications is really the centralization of control, the quality of service-based network analysis that you're going to get, and again, that ability to change routes based on that QoS data that you do get. Rapid reconfiguration of the network because the control plane is now centralized. Operators can make the decision of how to reconfigure the network on the fly if that's required. Detect intrusion attempts, develop virtual LANs and isolate networks, and also perform optimized swarm operations. So with software-defined networking, when you move the control plane out to a centralized location, what that allows us to do is basically set up their own local private networks so we can have collaborative or swarm operations, so virtual LAN, so that data can now be shared amongst maybe the 4 satellites that we're showing here, where previously it was sharing data together as the full network. So with software-defined networking, that gives you the flexibility to add nodes into the network, create your own virtual LANs, and then bring them back into the global whole network much easier than your traditional network of today. Of course, security. Networks and data protection go hand in hand. I mean, we all know about of the hacks that are going on out there, and so it's really important that the data through the mesh network is protected. And so you know, for most commercial programs and science missions, NASA's come out and said basically FIPS 140-2 level 1 security is something that's acceptable at the satellite level, and that you know, and the good news is that TUI has a product that is currently in development we call CryptoSwift, specifically designed to be FIPS 140 compliant, so that it meets those commercial program and science mission requirements. Also, from a government defense side, you know, a higher level of encryption rigor is required. So ultimately, with a mesh network, or really any space network, multiple security associations are required to support mesh networks as they change and as they evolve, or support other functions. And TUI also has a product line for that as well, which we call the CryptoSwift T1, that's in development, and we're hoping to deliver that Q3 of next year. So multiple security associations, I bring this up because when with multiple security associations, it allows for secure communications, not just as a global whole network, but also when the mission objectives change, and now you have to allow multiple missions to be performed as the network is reconfigured. Multiple security associations allow you to do that so that you can modify the security profile and have, for instance, that yellow, the nodes in yellow, be their own virtual LAN with their own security associations related to that. And so no one else knows what's going on in there, and that data can stay contained and protected. So in summary, mesh networks are ideal for resiliency, mission flexibility, data forwarding, swarm and collaborative operations, security, threat and intrusion detection, as well as performance. And SWIFT-LINQ is really an ideal solution that's available today and has a high TRL level for customers that are looking to do these types of operations. So at this time, we'll open it up to questions if anyone has any questions. So what ERP does SWIFT support? So we have, one of the things about our SWIFT radios is that they're very modular. So we have, we support UHF, LS, X, and KA band, and our, so each one of them has a different ERP, but one that we predominantly use for SWIFT-LINQ, which is our S-band radio, has a 33 dBm or 2 watt RF ERP. Hopefully that answers that question, Monty. And then I'm just looking at C2K JR Roca. When there are disruptions, DTM protocols used to be classical solutions to deal with that. You seem to have a different approach. Yeah. So one of the things that I'll say is that our customer came to us and basically one of their requirements to us was, we want to have the ability to have the network be able to have a node go off, perform a mission, and then come back and come talk to us. So one of the things that we wanted to have and really was a requirement is basically the broadcast or multicast functionality. So that's how we handled that for that. But we are looking at DTM protocols for our next gen parts. Let's see here. So let's see here for the next question. How do satellites discover routes? So it's a really good question. So ultimately with software-defined networking functionality, because the let me start higher than that. When you're putting a network of satellites together and you know exactly where they're going to be in which orbit when, and so that's one of the things that software-defined networking really gave us, is that there is a deterministic path of how satellites do connect to one another, and so we can have routing tables that are set up so that basically, depending on the location of where you're at, you can have a different routing table, and therefore you know which routes to talk to. Hopefully that answers your question there, Freeman. How many simultaneous connection satellites can be supported? That's a good question. So we can do up to 25 with SWIFT-LINQ in its current form, and we're working on growing the network to a much larger size here, to about roughly 10x that to 250 with our SWIFT HB platform. But with our current platform, we're somewhat limited to roughly about 25 units. And then from Gilberto, hello Gilberto, how's it going? What are the max data rates allowed by SWIFT-LINQ? So this is a great question. I love this question. So ultimately, Gilberto, the question, it's still a link budget problem. So it's going to be deterministic based on your antenna size, how much RF power is being put out, things like that. So if and how close the birds are. So ultimately, it's still a link budget problem. The SWIFT-LINQ doesn't solve physics. What it does is it allows radios to connect to one another much easier. So what we've been seeing though with our customer is about a megabit per second, but that's with 2 S-band patch antennas, basically giving us quasi-omnidirectional topology. So if you do go to a pointed antenna that has a lot more gain, you can definitely get that data rate up much higher. So what are the, I'm seeing another question here. What are the max distances allowed by SWIFT-LINQ, as well as RF frequencies? So we support UHF, L, S, X, and KA. And so max distances are really going to be, again, it's going to be up to your link budget and how big the antenna is. One of the things that we've, SWIFT-LINQ and its integration into our radio, what we're really trying to do is abstract the RF portion, or really the radio link, the layer 1 and layer 2 from our solution. So SWIFT-LINQ is capable of working with like a laser comm solution, for instance. So ultimately, I guess the answer to that is that it's still going to be a link budget calculation that has to be performed, and it's going to also be based on the technology that you're using for your level 1 and level 2 physical layer. ModCods, that's great. So we support, natively we support BPSK, QPSK, OQPSK, 8PSK, and 16APSK, as well as all the standard CCDS codings as well. Convolutional, Reed-Solomon, Viterbi, LDPC are all supported. Next question here. How does routing depend on attitude control since you use directional antennas? So that's a great question, Freeman. So our first solution actually doesn't have directional antennas. We're actually using 2 S-band patches, one on each side of the satellite. So we're essentially getting what we've kind of dubbed quasi-omnidirectional coverage, which, you know, obviously there's going to be some voidage with the patch antennas, but so that's our first solution. But as you move to directional antennas, the routing, it gets a lot, believe it or not, it gets a lot easier, even though it's still a pointing problem. But ultimately, you're typically pointing to one other device that's in your orbit, and you know where it is. So you have that kind of that pointing vector azimuth and elevation that you know where you're going to point to, if that makes sense. And then Tom, what sort of latency could you see if you had message hopping from satellite link to a ground device and transferred to a ground station halfway around the Earth? What kind of hopping from satellite link to a ground device and transferred to a ground station halfway? So Tom, I think I'm going to try to interpret this question. So what's the latency that we're seeing from a satellite to the ground, and then to another node halfway around the Earth, I think is the question. So ultimately, the TD our system uses TDMA multiplexing. So ultimately, all of those TDMA characteristics are adjustable in our system. So slot times, guard times are all adjustable on the fly in orbit. So you can make the determination of how much latency versus throughput that you want. So you can have your windows be much larger and have a bunch of data come down when each radio gets to talk, and then also be able to also shorten them up so you have very small latency, if that makes sense, Tom. Oh, okay. Let's see here. What sort of latency could you see if you have a message hopping from a satellite linked to a ground device and transferred to a ground station halfway around the Earth? For example, how many seconds does it take for an IoT sensor in Hawaii to be received in Munich? Yeah, so what's great about SWIFT-LINQ is that's going to depend on how big your mesh network is and how big your how close you are to the ground, obviously. So that's a tough question, Tom, to answer because there's a lot of calculations to see there. But essentially, if it's riding through the mesh network itself, it could be anywhere. Our latency that I was talking, our throughput that we were talking about for 1 megabit per second was through the entire chain from one device hopping through another device. So that's a really good question, and I guess I don't have an answer off the top of my head because I'd have to do some math there. Any other questions? Okay.
So if you guys want to reach out, we have some slick sheets and some information that we can send you on SWIFT-LINQ. If you guys want to connect further, that one-on-one meeting as well, we can do that. So I'll just put that email address in the chat here, and you guys can reach out to us if you'd like. There we go.
Thanks for joining us today, guys.
Yeah, thank you everyone that came. We have a talk tomorrow on in-space services at the same time. So if you guys want to join us for that too, we'd be happy to see you. So thank you for coming.